In the previous lectures, we have studied about vector differentiation called as a gradient and divergence and curl operation. Okay, so all these operations are called as a spatial differentiation. So whenever we see the differentiation, we need to know, is it a first order differentiation or a second order differentiation, or what is the order of the differentiation. Okay, so here gradient, divergence, curl we apply only once, that is called as a first order differentiation. If you apply differentiation twice, 2 times, then it is called as a second order differentiation. Okay, so till now we have studied about first order vector differentiations. Now we will see what is the second order vector differentiation. Okay, for that let us consider what are the differentiations we have studied are gradient. So we know that the gradient is applicable only on scalar fields, the gradient of a scalar. Okay, next we have studied divergence. Divergence is a dot product, should be applicable only on vector fields, divergence of a vector. Okay, next we have studied about curl operation, curl. Okay, so curl is a application of cross product, so cross product should be applicable only on vector fields. Okay, so these are the 3 first order differentiations we have studied. Okay, so now if you apply differentiation second time on this one, so on this any of these operations, that is called as second order differentiation. Okay, now what is the second differentiation we can apply on this one? We know 3 operations: gradient, divergence, curl. Okay, let us apply all the 3 differentiations as a second differentiation on each of them. Okay, so then we are going to get like this. First I will apply gradient as a second differentiation, then I will apply divergence as a second differentiation, and I will apply curl operation as a second differentiation. We got 3 combinations. Okay, similarly same combinations we apply on next 2. Okay, so we apply gradient as a second differentiation and divergence as a second differentiation, then we apply curl as a second differentiation. Next we do same, apply gradient as second differentiation and divergence as a second differentiation. Next curl as second differentiation. Yeah, so from 3 first order differentiations, if you apply all the combinations of second order differentiations, we got 9 combinations. Okay, among all these 9 combinations, we need to find which are valid second order differentiations and which are invalid second order differentiations. Okay, then we will discuss in detail about that valid second order differentiations. Okay, let us examine each one by each one. So here first come to these combination. Okay, so here del is a vector and this is a scalar. What is a vector into scalar? Vector into scalar will give us again vector. Again vector. Okay, that means always a gradient of a scalar is a vector quantity. Okay, gradient of a scalar is a vector quantity. Gradient of a scalar is vector quantity. Now just see here, on this vector quantity we are applying gradient. Okay, is it possible? We know that the gradient is applicable only on scalars, so it is not possible. Or we can see like this. So del is a vector and here is another vector. 2 vectors cannot be multiplied directly. Okay, so in these 2 point of views, this is a incorrect one. Okay, or it is not a valid second order differentiation. Next, so here it is a vector, we are applying divergence on vector. Okay, so divergence is applicable on vectors, so it is a valid. Or we can say that dot product is applicable between 2 vectors. Del is a one vector, there is another vector, we can apply dot product between these 2 vectors. Okay, so this is a valid second order differentiation. Okay, next one, here there is a vector quantity. On this vector quantity we are applying curl operation. or we are applying cross product between two vectors. Okay, so this is a valid second order differentiation. Okay, similarly come to the next column. Here we have divergence of a vector, okay, or there is a dot product. What is the results of any dot product? Scalar. Results of dot product is a scalar, or divergence of any vector is scalar. Okay, so now just examine second order differentiation on this quantity. So may I apply gradient on scalar? Yes, a vector and scalar can be multiplied directly. So this is a valid second order differentiation. Okay, next one. Here there is a divergence. May I apply divergence on a scalar? No. Okay, dot product cannot be applicable between vector and scalar. Dot product is applicable only between vectors, two vectors. Okay, here there is a scalar, so this is a invalid combination or invalid second order differentiation. Okay, next one. May I apply curl operation on scalar? No, not possible. Curl or cross product is applicable only on vectors. Okay, so this is the invalid combination. Okay, so come to the last column. Here we have curl of a vector, or there is a cross product. Okay, so what is the results of any cross product? Results of any cross product is vector. It is a vector. Yeah, this is a vector quantity. Curl of a vector is again vector. Now let us examine second differentiation on this quantity. So here, may I apply a gradient on a vector? No, it is not possible. Gradient is applicable only on scalars. Okay, or two vectors cannot be multiplied directly. So this is a invalid second order differentiation. Okay, so next one. Here we have divergence on a vector. We can apply divergence on a vector, or we can apply dot product between two vectors. Okay, this is valid. Next one. So curl of a vector, we can apply curl operation on vector quantity, or we can perform cross product between any two vectors. So this is also valid second order differentiation. Okay, so now just see here, from these 9 combinations of second order differentiations, only 5 are valid second order differentiations. Okay, so here I give numbering. Here first valid second order differentiation, second valid second order differentiation, this is third valid second order differentiation. So here it is a fourth one and also fifth one. Okay, so only these are the 5 valid second order differentiations. Okay, so now let us see, let us deeply examine what are these 5 valid second order differentiations one by one. Okay, now consider first valid second order differentiation, that is divergence of gradient of a scalar. Divergence of gradient of a scalar. Okay, here let me consider any scalar quantity here. So here I write divergence of gradient of, in the place of scalar I consider any scalar function f. Okay, so now let me expand this one. So here, what is the formula for del operator? Del operator is given by dou by dou x into x cap plus dou by dou y into ay cap plus dou by dou z into az cap, dot product. So I have written this del operator. Next, gradient of f. Okay, so what is the formula for gradient of f? Dou by dou x of f into x cap plus dou by dou y of f into ay cap plus dou by dou z of f into az cap. This is the gradient of f. Now we need to perform a dot product between these two vector quantities. Okay, so you know that how do we evaluate dot product? Multiply similar components. Okay, so just multiply x components. Okay, so we get dou by dou x into dou by dou x of f plus multiply y components, that is dou by dou y of dou by dou y of f plus multiply these z components on both the vectors. Dou by dou z, dou by dou z of f. Okay. Here in each term we are applying differentiation second time. Okay. So will become dou square dou x square of f plus second term dou square dou y square of f plus dou square dou z square of f. This is the right side equation. Okay. The left side, if you observe this one, this del dot del will become del square of f. Okay. So we say that del square of f is equal to this is the equation. So this is the first valid second order differentiation, and here this operation del square is called as a Laplacian operator. Laplacian operator. Okay. So Laplacian operator can also be said as a divergence of gradient of. Okay. So divergence of gradient of can be called as del square and can be called as a Laplacian operator. Okay. Here what you need to observe here is this Laplacian operation is applied on which quantity? F is a scalar. So the Laplacian operation is applied on a scalar quantity. Fine. Then if you apply Laplacian on a scalar, what is the results? Okay. See this right side equation. Is there any direction parameter? No, there is no x cap, there is no ay cap, there is no az cap. Okay. So there is no direction in this right side equation. So it is a scalar quantity. Okay. So we say that results is also a scalar field or scalar quantity. Okay. So that means we apply Laplacian on a scalar and results is also a scalar. Okay. So but here there is one important point you need to observe here. The Laplacian operation is the only operation which is applicable both on vectors and also scalars. Okay. Here I have shown you Laplacian is applicable on scalars, results is a scalar. But this Laplacian can also be applicable on vectors and results is again a vector. Results is again vector. Now let me explain how we can apply this Laplacian on a vector quantity and what is the equation for that. Okay. Now consider this del dot del. Okay. So here we need to perform dot product between these del operators. As we know that del is given by dou by dou x into x cap plus dou by dou y into ay cap plus dou by dou z into az cap dot dou by dou x into x cap plus dou by dou y into ay cap plus dou by dou z into az cap. So here we are performing dot product between two similar vectors. Okay. So then just we know that how do we perform dot product? Just multiply similar components. Okay. If you multiply x components, we get dou square dou x square plus multiply y components dou square dou y square plus multiply z components dou square dou z square is the right side results. Then if you see the left side, del dot del will be called as a del square, which is called as a Laplacian operator. Okay. Now you just tell me this del square is a vector quantity or scalar quantity. So if this del square is the results of some dot product. Okay. Results of dot product is always a scalar quantity. Okay. Or you can observe the right side equation. In this right side equation there is no direction parameters. So there is no x cap, no ay cap, no az cap. Okay. So the right side parameter is also scalar. So finally I conclude here del square is a scalar quantity. Okay. Now you can easily observe that a scalar and vector can be directly multiplied. You know that. So what I do here is a scalar del square can be directly multiplied with a vector quantity. Vector quantity. A scalar and vector can be directly multiplied. What is the results? When we multiply any vector with scalar, results is again vector. That's what I have explained. We can apply Laplacian operation on vectors also, but results is again vector quantity. Okay, so let me explain with some vector here. So del square, in the place of vector I consider a bar. A bar is the vector. Okay, so del square, vector a bar can be represented in terms of its components. There is ax into ax cap plus ay into ay cap plus az into az cap. Yeah. Now this scalar can be multiplied. Del square is a scalar. This scalar can be multiplied with each term of this vector a bar. Okay. So I say that del square of ax into ax cap plus del square of ay into ay cap plus del square of az into az cap. Now just observe each term here. In each term we have del square of ax. Again it is a Laplacian on some component x component ax. Okay, it just looks like a del square f. Okay, so then how would I write formula for this one? Here we need to expand each term like a Laplacian on a scalar. Okay, so where del square of ax is equal to dou square dou x square of ax plus dou square dou y square of ax plus dou square dou z square of ax. Just a Laplacian on ax. Okay. Similarly, the second term, this is del square of ay. There is a dou square dou y square of ay plus, this is a x square. Dou square dou x square of ay, dou square dou y square of ay plus dou square dou z square of ay. Just a Laplacian on y component ay. Okay. So similarly, Laplacian on az, that is dou square dou x square of az plus dou square dou y square of az plus dou square dou z square of az. Okay. So combinedly this is a expansion for the Laplacian on a vector a bar. Okay. So Laplacian on a vector a bar is given by this equation. So in this equation each term can be evaluated with the help of the Laplacian on a scalar field. Okay. So this is the way how we can apply Laplacian operation. So this is the first valid second order differentiation. Okay. Now let us go for the second one. What is the second valid second order differentiation? So here is the second valid second order differentiation. So first one we have studied about Laplacian operation. Okay. So next one is here it is the curl of gradient of a scalar. Okay. So here let us consider any scalar function here. First I will evaluate this equation. We will obtain some results. According to results we give name for this equation. Okay. So here the curl of gradient of a scalar f. Let us consider in the place of scalar I consider f here. Okay. So now let us expand this curl operation. So how do we evaluate any curl operation? With the help of determinant. So let us write a determinant here. You know that first row must be unit vectors ax cap, ay cap, az cap, and second row is a components of first vector. First vector in the cross product is del. Components of del are dou by dou x, dou by dou y and dou by dou z. Okay. And the third row of this determinant is components of a second vector in the cross product. What is the second vector in the cross product? Gradient of f. Okay. What are the components of gradient f? Dou by dou x of f, dou by dou y of f and dou by dou z of f. Okay. So let us evaluate this determinant here, which is equal to, so ax cap into this ax cap is multiplied with dou by dou y of dou by dou z of f. This is the second differentiation we are applying on this one. Okay. minus dou by dou z of dou by dou y of f. Let me write here. We have dou by dou y of dou by dou z of f minus dou by dou z of dou by dou y of f is the x component. Okay. Now, similarly, expand this one minus ay cap into dou by dou x of dou by dou z of f minus dou by dou z of dou by dou y of f plus az cap into dou by dou x of dou by dou y of f minus dou by dou y of dou by dou x of f. Yeah. So, like this we expand this, we evaluate this determinant. Now, observe this one. Here we are applying second differentiation dou by dou y and dou by dou z, okay, which will be equal to, here it is, ax cap into will be dou square dou y dou z of f minus this will be dou square dou z dou y of f minus ay cap into dou square dou x dou z of f minus dou square dou z dou x of f plus this last term dou square dou x dou y of f minus dou square dou y dou x of f, yeah, into az cap. Yeah. So, now just observe this equation. Can you tell me, is there any cancellations here? Yeah, absolutely. So, here already we know that, so this partial differentiation, second order differentiation dou square dou x dou y on any quantity f must be identically equal to dou square dou y dou x of f. That means here the order does not matter when we apply partial differentiation. You may apply first dou by dou y, then dou by dou x, or you can apply dou by dou x first, then dou by dou y. Okay, this order does not matter. So, the second order differentiations are identical, equal, or same in the case of partial differentiation. Okay, so according to this one, we say that, so these two terms are same, which gets cancelled. Okay, again these two terms are same, which gets cancelled, and these two terms are same, which gets cancelled. Then what is the final results? Okay, I will write here. Left side equation is, this is the curl of gradient of f, which is equal to, the right side term is 0. Okay. So, actually what we have obtained is, this is nothing but curl of gradient of a scalar, some scalar, which results 0. I write the same thing, the curl of gradient of any scalar field or scalar function is equal to 0. Okay. So, this equation is called vector null identity. Vector null identity. Okay. So, this is a very important one. So, this is the second valid second order differentiation, which is named as null identity. So, many times it appeared in the exams as a word statement. The word statement is the curl of gradient of any scalar is always equal to 0, is called vector null identity. Okay, whenever we get this combination of equation in electromagnetic fields, we directly according to null identity, we put it as 0. Okay, so the same statement can also be written in some other form. Just observe this one. What is this quantity? So here del is a vector. Vector multiplied with scalar will give you again vector. So this quantity is a vector quantity completely. This is vector quantity. And write the remaining equation as it is. Curl of this vector quantity is equal to 0. So whenever we have, whenever we obtain a equation like this, curl of any vector is 0, then without changing these results, the vector can also be replaced with the gradient of a scalar. Then it becomes a null identity, results remains same. Results will remain same. Okay. So another form of statement for null identity is that, so if curl of any vector is 0, then the vector can be replaced with gradient of a scalar according to null identity. Okay. This is another form of statement. Okay. So this is the second valid second order differentiation. Next we go for third one. So till now we have studied about second order vector differentiations. First second order differentiation we have studied is divergence of gradient of a scalar, which is also called as Laplacian of a scalar. This is we have studied. Next, second valid second order differentiation is, that is curl of gradient of a scalar, which is always 0, is called as a null identity or vector null identity. Okay. Next, third one. Third one is gradient of divergence of a vector. Yeah. So actually for first two we have a special results, that's why we have a special names here. First one is Laplacian operator, second one is null identity. For the third one there is no special results, that's why we don't have any special name for this third one. So we just read as it is. Okay, there is a gradient of divergence of a vector. Okay. So next fourth one. Fourth one is divergence of curl of a vector. Divergence of curl of a vector. Okay. So let me explain what happens results of this equation. From the results again we give name for this one. Okay. So now let me explain the fourth one. So the divergence of curl of any vector, I consider vector is a bar. Vector is a bar. Okay. So now let me expand this one. So we have del operator. Del operator is given by dou by dou x into x cap plus dou by dou y into a cap plus dou by dou z into az cap. This is del. We have del dot. Next we have curl of a bar. Generally we evaluate this curl operation or cross product with the help of determinant. Okay. So first row must be unit vectors, ax cap, ay cap, az cap. Second row should be components of first vector in the cross product. There is a components of del, dou by dou x, dou by dou y, dou by dou z. Okay. Next one is a bar. Components of a bar, ax, ay, az. Okay. So now we need to evaluate a dot product between the del vector and curl of a bar. Just we do multiplying x components and multiplying y components and multiplying z components here. Okay. So let us write here. What is x component in the first one? Dou by dou x is the x component in first vector. What is x component in second vector? X component is the term multiplied with ax cap. The term multiplied with ax cap is dou by dou y of az minus dou by dou z of ay. Okay. I write dou by dou y of az minus dou by dou z of ay is the first one. Next, so next y component, multiply y components in both the vectors. For first one, y component is dou by dou y. In the determinant, y component will always have negative sign, so write minus of, so dou by dou x of az minus dou by dou z of ax. Dou by dou x of az minus dou by dou z of ax plus multiply z components. Okay, here z component is, in z component in the first vector is dou by dou z. In the second vector, z component is az cap is multiplied with dou by dou x of ay minus dou by dou y of ax. Yeah, just let us simplify this equation. Then we find the results and we give the name for this one. So here, so we are applying differentiation second time on az. Okay, so this multiplication will give us dou square dou x dou y of az minus dou square dou x dou z of ay. Then again minus dou square dou y dou x of az. Then here minus of minus will be plus. Okay, so dou square dou y dou z of ax. Okay, plus. Okay, so dou square dou z dou x of ay minus dou square dou z dou y of ax. Okay, this is the entire equation. So let us observe, is there any cancellations here? Okay, so just observe dou square dou x dou y. Here dou square dou x dou y, dou square dou y dou x, both are same. Both the differentiations on az and with opposite sign. So these two gets cancelled. Okay, then consider dou square dou x dou z, dou square dou z dou x, both are on same parameter ay. So these two gets cancelled. Okay, so next dou square dou y dou z, dou square dou z dou y on ax, these two are same, these two gets cancelled. Okay, so what is the final results? We obtained divergence of curl of a bar. Right side equation is 0. Okay, when it is 0, what is the name we can give? When results is 0, it is a null identity. Again it is vector null identity. Vector null identity. Okay, so just write in general form, in the place of a bar, what do we have? Vector. Okay, I write divergence of curl of any vector is always equal to 0, is called null identity or vector null identity. Vector null identity. So here, so we write a word statement for this one. So word statement is the divergence of curl of any vector is always 0 and is called null identity. So till now we have studied two null identities. One is a curl of gradient of any scalar is always 0. Another one is a divergence of curl of any vector is always 0. Okay, these are the null identities. Two null identities we use in the electromagnetic fields. Okay, so let us see what is the other form of statement for this one. So just see here, what is this quantity? There is a cross product between two vectors. Always cross product will result vector. So this entire quantity is a vector quantity. This is a vector quantity. Okay, remaining equation is as it is. Okay, from this we write another statement for null identity. So whenever you have divergence of any vector is equal to 0, Okay, without changing these results, the vector can be replaced with curl of another vector. Whenever you replace this vector with the curl of another vector, it becomes a null identity and results remain same, 0. Okay, so without changing these results, this vector can be replaced with curl of another vector. Okay, so the statement will be, if divergence of any vector is 0, then the vector can be replaced with curl of another vector according to null identity. Okay, so this is the fourth valid second order differentiation. Okay, so we have studied first 4 second order vector differentiations. Now consider fifth one, the last one. So fifth valid second order differentiation is the curl of a vector. Curl of a vector. Okay, so this is another important one. If you just observe this one, so here this I will tell you a simple way to write this equation. So this equation is given by 3 minus 1. Okay, so there are, if you observe the previous 4 second order differentiations, among the 4, 2 are zeros. So this is 0 and this is 0, both are called as null identities. Okay, what are the non-zero equations for second order differentiation? This third one and also first one. Okay, so consider these two non-zero equations and 3 minus 1. Okay, so this is given by, what is the third one? Third one is gradient of divergence of a vector. Gradient of divergence of vector. What is the first one? Minus, actually this is a Laplacian operator. So here it is shown that Laplacian on a scalar. Okay, and you know that the Laplacian operation can be applicable on both vectors and also on scalars. Okay, you just tell me here I should apply Laplacian in the second term right side. It should be on vectors or scalars. Okay, so that depends upon, so what is the left side quantity is. Okay, so here you know that whenever you have a curl of a vector, the cross product will result a vector. Okay, again there is a cross product, again this cross product will also result a vector. Okay, so the left side quantity is a vector. Okay, so the right side quantities should also be vectors. Okay, so then if you want to get this term as a vector, I should apply Laplacian on vectors or scalars? I should apply only on vectors. Laplacian of a vector will give us again vector. Okay, that's why it is Laplacian on a vector. Okay, so this is the equation for curl of any vector. Curl of any vector. Okay, so let us write this one as a formula. So generally we use this equation as a formula. That means I need equation for what is a curl of a bar. What is the equation for this one? Okay, so this is equal to, as I said, third equation first, that is gradient of divergence of a bar minus Laplacian on the same vector a bar. Okay, so this is an important equation. You can take it as a note. Okay, so these are the 5 valid second order differentiation we need to understand. First we have studied about first order vector differentiation, gradient, divergence and curl operation. Okay, now we have studied about a second order differentiation, Laplacian operator and 2 null identities and gradient of divergence of a vector and curl of a vector. These are the 5 important second order differentiations we use in electromagnetic fields directly as a formulas. Okay, so let us do a problem on this one. We take a problem. Now let us do a problem. So here a vector field A bar is given to us. A bar is 9y square z minus 6kx into x cap plus 13x square z minus 8y ay cap minus 17x square y minus 4z az cap is a vector field. Okay, if A bar can be written as a curl of another vector, then what is the value of k? Okay, so what is given in the question is a vector field A bar is given to us, and we said that vector A bar can be written as curl of another vector. I consider another vector F bar. Okay. If A bar can be written as curl of another vector, then what is the value of K? Okay. So just consider this equation that is given in the question. Let us apply divergence on both sides, just like differentiate on both sides. Okay. So apply divergence on both sides. So divergence of A bar is equal to divergence of curl of F bar. Now just observe what is the equation right side we have. So here we have divergence of curl of a vector F bar. Already we have studied that divergence of curl of any vector is always equal to 0, and it is called as a null identity, vector null identity. Okay. So according to null identity, this term will become 0 because it is a null identity, vector null identity. Okay. So then the equation that results is divergence of A bar is equal to 0. Okay. So if generally we know that second statement of null identity, if divergence of any vector is 0, then the vector can be written as curl of another vector. Okay. Or you take vice versa statement. If a vector can be written as curl of another vector, then its divergence is equal to 0. Okay. That's what we obtained here. So now, so from this given statement, divergence of A bar is 0. So let us find what is the value of K. Okay. What is the formula for divergence of A bar? Dou by dou x of Ax plus dou by dou y of Ay plus dou by dou z of Az is equal to 0. Now substitute x, y, z components of A bar here. So if you observe this one, so this term multiplied with Ax cap is the x component, and this is the term multiplied with Ay cap is y component. Here it is including negative sign. This term multiplied with Az cap is z component. Okay, just substitute in this equation. So we get dou by dou x of x component is 9 y square z minus 6kx plus dou by dou y of y component is 13 x square z minus 8y plus dou by dou z of minus of 17 x square y minus 4z. This entire equation is equal to 0. Yeah. Now you know that all are partial differentiations in this equation. Dou by dou x differentiates only x term, and dou by dou y differentiates only y term. Dou by dou z differentiates only z term. Okay, differentiation on remaining terms will be equal to 0. So we get this is minus 6k. So this is minus 8, and here it is plus 4, which is equal to 0. Okay, then 6k is equal to 4 and k is equal to 4 by 6 or 2 by 3. Okay, so the answer is 2 by 3. So k value is 2 by 3. Okay, so this is about second order vector differentiation and a problem on second order vector differentiation. Okay, so till now we have studied about so only vector differentiations. So first order 3 first order vector differentiations and 5 second order vector differentiation. Okay, so next very important thing we need to understand in this vector calculus is so divergence theorem, Stokes theorem, and also theorem on gradient. Okay, these are the very important concepts. Next we see the what are these important theorems we use in electromagnetic fields.